Okay, so today we're going to finish up chapter 33. So we're mostly going to spend the time looking at polarization and polarizing filters, and then just a little bit of scattering. But polarization is the main point here in today's lectures. So polarization is technically a characteristic that all transverse waves have, but typically when we're talking about like a transverse wave on a string, we don't really need to talk about the polarization. We usually care about polarization more when we're looking at EM waves specifically, since electromagnetic waves are a vector in nature. It's more typically more common to only talk about polarization when we're talking about EM waves. So the polarization just refers to the direction of the electromagnetic field vector. So we already saw for our, when we have an E and B field in a wave, the electric field and the magnetic field both have a direction associated with them since they're both vectors. So the polarization of an EM wave is just the direction of the electric field vector. So in this case, this is J hat, so our wave is polarized in the J or the Y direction. And it's always the electric field vector that defines the polarization, never the magnetic field vector. Since typically when we have a wave, we remember that the electric and magnetic field are perpendicular to each other, and that E cross B will give you the direction of travel. So if you know the polarization of the electric field and you know the direction of travel for the wave, the magnetic field direction you can figure out right away. So the polarization always just refers to the electric field direction. Okay, so here we have just a picture. So in this case, you can see that our electric field is oscillating in the Y direction. So as we just had in the previous slide, this is polarized in the Y hat or the J hat direction. And then the plane of oscillation right here is just the YX plane, because it's oscillating in the Y direction, but moving in down the X direction. So the YX plane here is just the plane of oscillation. Okay, so then we can have also unpolarized light. So when you have a light bulb or the sun, that produces unpolarized light, or sometimes you'll also see it called randomly polarized light, because the light waves are in all different directions. They're polarized in all 360 degrees that you can have, which is shown down here. So the light from the sun or the light from a light bulb has electric field vectors that are just polarized in every possible direction. They're not polarized in just a specific direction. They're polarized in all directions. So that's called unpolarized or randomly polarized. Now, this is different when you have like some kind of antenna, or typically when you want to send out electromagnetic waves, they'll be polarized in a specific direction. So when you have a radio tower, the waves are vertically polarized in the same direction as the antenna, so the waves will all kind of be coming out, like that, sort of along that same axis as the antenna itself. So those are polarized in a specific direction and vertically polarized. Okay, and then we can make polarized light from unpolarized light. So if we have unpolarized light, we can send it through what's called a polarizing sheet or a polarizing filter. Sometimes you'll also see those called Polaroids, but we'll be using polarizing filter in this class. So basically all those do is they're made out of some material that has like these lines down it. Now we're not going to get into how they polarize things, but it basically is a transparent sheet that only allows certain components of the electric field to pass through. So if you have a sheet that has have like vertical lines going down, only the components of the electric field in that vertical direction will be able to pass through, and everything else will get blocked. So obviously we'll see pictures of this in a second. And so what these do is the light on one side of the filter is unpolarized, and then it passes through this polarizing filter, and then only the polarized light all in one direction comes out on the other end. So the way that works, here's a little picture. We have our unpolarized light, that's in every direction coming here, and then it hits this polarizing sheet, and it has these like slats going through it, which are typically like a certain type of molecule stretched out. So you'll have these little lines down it, and then only the vertically polarized components of the unpolarized light here, so only those vertical components will make it through the polarizer. Everything else, if it's like this horizontal component here, that will get absorbed. So then you have polarized light come out the other end of the polarizing filter, and now you have polarized light as opposed to unpolarized light. Now typically you want to know the intensity. When we have polarizing filters, we want to know the intensity of the light beforehand and afterwards that gets through this polarizing filter. So when we have unpolarized light, which we're denoting by I naught, so our unpolarized light with intensity I naught, the light that emerges from the filter will be exactly half as intense as the light going in. So our intensity on the other side of the polarizing filter is exactly 1/2 the intensity of the original unpolarized light. And now you can think about that. Obviously, you can show all this stuff with Maxwell's equations, but one kind of easy way to think about that is if we have unpolarized light here, which is in all directions, you can rewrite it in terms of just y and z components. And then, so this is our unpolarized light now, which has both a y and a z direction. And then you can see that if we have just here our y and z direction, only the y components will get through our polarizing filter, and the z components will get absorbed. And if these have the same magnitude, you can see here that all of these vectors are the same length, so they all have the same magnitude. Since the y and z direction, the y and z components here, have the same magnitude, only half of the light gets through, basically. So our intensity over here is I naught, and our intensity over here is 1/2 I naught. Now we can, let's see what happens if we send polarized light through a polarizing filter. So if we have polarized light that's already polarized in some direction, let's say here, it's polarized sort of in this, diagonal direction, and we want to know, well, how much of it is going to get through this polarizing filter that's polarized vertically, right? So it's in the y-axis here. So the first thing is we know this has intensity. This has intensity, initial intensity I naught, this light over here. And then we can see that, we can kind of guess that only the y component of this full vector here is going to get through. So what's the y component of this vector? Well, if we look at this angle here, the y component is the adjacent side, so that's going to be cosine. So our light that gets through is going to be E cosine theta, right? And now think back to one of our previous lectures where we did the intensity of a electromagnetic wave. One of the equations we had was that the intensity was equal to E squared over C mu naught. So our original intensity is the magnitude of this electric field here squared over C mu naught. Now our new intensity is going to obey the same equation, except now our E, instead of being the full magnitude of our electric field vector, is just the y component. So we're going to replace that with cosine, right? So I just replaced E with E cosine and then squared over, C mu naught. And now if I want to find the ratio of these two intensities, so I want to do I over I naught to find the ratio of the intensity of the light that passed through compared to the light that was incident, I can just do a ratio here. So I have E squared cosine squared over C mu naught over E squared C mu naught. And then we can see here that our E's will cancel, and then our C mu naughts will cancel, right? And so this just comes out to cosine squared theta. So I can just rewrite this equation here as the final intensity after it passes through the polarizing filter is equal to the original intensity times cosine squared theta. So now I have an equation that says whatever my original intensity is, multiply it by the cosine squared of the angle between the electric field vector and the polarizing direction, basically. And that will give me the intensity of the light that passes through that filter. Okay, so I just rewrote that here. Now the most important thing here is a lot of times you'll see, let's say we have this polarizer, and let's say it has lines that are going like this, okay? So a lot of times you'll see, so the angles here, a lot of times you'll see they'll say like a polarizer has an angle theta or whatever it is. That's not the angle here. This angle is the angle between the polarizer and the electric field. So if my electric field that was incident was actually, let's say, like in this direction, okay, so if it was horizontal, phi would actually be here. It would be the angle between the polarizer and the electric field, not just the angle of the polarizer. Because a lot of questions will just say the polarizer is at some angle, find the intensity of the light. So you have to be very careful that you're actually looking at the angle between the electric field and the polarizer. But like I said, we're going to do a bunch of problems with this, so you'll see how this works in a second. Okay, so let's look at just some qualitative examples. So here we have unpolarized light goes through a polarizing filter. So we already know that half of it gets through, right? So we have half of the intensity over here. Now it goes through another polarizer. So now we're going to be looking at the electromagnetic field was this way, and then these are polarized in this direction. So this angle here, you'll do the intensity of this light times the cosine squared of that angle right there, and that will give you the new intensity that comes out of the two polarizers at the end. And you can see here, these are like, you'll see a lot of times polarizing sunglasses are used to like reduce glare, but if you take two polarizing sunglasses and hold them at 90 degrees, they actually don't let any light through. So if instead this polarizer, let's say, was polarized in this direction, instead it was polarized horizontally, what you would have here is at this polarizer you would get 1/2 I naught, right, from the unpolarized to polarized, and then between this polarizer and this polarizer you would have the 1/2 I naught, and then you would have cosine squared of 90 degrees because the angle between the electric field and the polarizer is 90 degrees now. So you'd have cosine of 90, and cosine of 90 is 0. So actually no light at all would get through. The intensity of the final light would be 0, which means there's no light. So that's what happens here, why these two sunglasses together, when you hold them at 90 degrees, are just completely black and don't let any light through. And it's actually really cool. It's too bad we're not in person, but if you can, normally would be able to get like actual polarizing sheets, and it's really cool to be able to, hold them up and move them, and you can see that as you move them to 90 degrees, they just become black and you can't see through them. And then if you move them so that they're, in the same direction, you can see through them. So it's like kind of trippy to see. So it's a shame that I don't have polarizing filters here, but if I did, maybe you could find some videos on YouTube or something, because it's pretty cool. But anyway. Okay, so now let's do a sort of conceptual question. So here we have an unpolarized light, like we had just before. So unpolarized light is incident on two crossed polarizers. No light is transmitted. A student asserts that if a third polarizer is inserted between the other two, some transmission will occur. Does this make sense? How can adding a third filter increase the transmission? So this is a good problem to think about for a couple seconds on your own. Okay, so this one, like I said, is very similar to our previous problem. So let's do this. So we have a polarizer here that's this way. We have another polarizer here that's this way. So we know no light gets through. If we have unpolarized light, we have a little... Oh, that's ugly. We have unpolarized light coming through this way. We know that if they're at 90 degrees, when we have that cosine squared of 90, that the final intensity here will be 0. So how can we get light to go through them? Well, if we add a third polarizer in between them, we can actually make the light on the other end not 0. So if we add a third polarizer that's actually diagonal, that's at 45 degrees, then light will get through. And we can see this. So let's see. From this unpolarized light to here, we know that the intensity decreases by half, right? So from here to here, we have 1/2 I naught, right? And now, once it passes from here over this second filter, so in here, it will be 1/2 I naught, because that's the intensity that now is going into this filter, and then times cosine of 45, right? Because now this polarizer is at a 45-degree angle, and the light coming from here is polarized vertically, right? So this light is polarized vertically. This one is at now a 45-degree angle to this light. So we have 45 here. So this will just be 1/2 I naught, and then cosine of 45 is square root 2 over 2. So we'll get 2 over 4. So you can actually see another 1/2 of the light gets through. And then now the light that emerged from here is polarized in this 45-degree angle. So now the angle between this light and this polarizer is actually 45 degrees now instead of 90. So now we have another, we'll take this intensity, because now this is the intensity that was hitting that third filter. So we have 1/4 I naught, and then we have another cosine of 45 there. So we can see here that it's not 0, right? This is actually going to be 2 over 4 again. So you can see here that by adding a third polarizer in the middle, instead of now having the light go from 0 degrees to 90 degrees, which will give you cosine of 90, which is 0, now you have 0 degrees to 45 degrees, and then another 45 degrees. So you don't get that cosine of 90 anymore, you're just using cosines of 45, so you can actually pass light from here to the other end by just adding a third filter that's at a diagonal angle. So this is also really interesting if you take like quantum mechanics or something. I'm sure a lot of you have heard that quantum mechanics is all basically probabilistic, and everything's essentially a probability. And this is like a example of that. That's in real life, where we can see sort of these like macroscopic effects of these like quantum probabilities, because what's really happening here is a probability. When the unpolarized light passes into the first filter, the probability per photon that it will actually make it through the filter is 1/2. So if you throw a bunch of photons through, you get half of them end up going through. Then if you didn't have this this middle filter here, the probability that a photon would then make it through this filter would be 0. But by adding this third filter in the middle here, each photon here that passes through this filter now will have a 1/2 probability of making it through, and then now it will have again a 1/2 probability of making it through this filter. So you're really just kind of playing around with the probabilities here, and that's why this works. All right, so anyway, let's go on to another problem. So here we'll do a more quantitative example. So here we have the incident unpolarized light in this example here, or this figure, has intensity I naught. So this light has intensity I naught. Find the intensities transmitted by the first and second polarizers if the angle between the axis of the two filters is 30 degrees. So we can see here this first one is 30, phi here is 30 like off the vertical. So we have 30 degrees initially here. And then this one is vertical again. So the difference between this polarizer and this polarizer is just 30 degrees. Okay, so let's do for the first polarizer. So for the first, we know that the intensity is just going to be 1/2 the initial intensity, right? So that's all we have to do for the first one. It doesn't matter what this angle phi is. It just has a 1/2 probability of getting through if it's initially unpolarized. Then, so now in here, we have this light in here has I naught over 2, right? It's 1/2 the initial. So now we have light with intensity I naught over 2 passing through this filter. but this light now is polarized at like a 30-degree angle, right? Because it passed through this filter. So now the angle between the light that's about to pass through this polarizer now is 30 degrees, right? Because this one's polarized at 30, and this polarizer filter is at 0 degrees, so we have a difference there of 30 degrees. So then for our second filter, we have I is equal to I naught cosine squared theta, but the I naught here is this 1/2 I naught, right? Because that's the intensity of the light that's about to hit that second filter is 1/2 I naught, and then cosine squared of 30. So we have 1/2 I naught, and then cosine of 30 is square root 3 over 2 squared. So we get 1/2 I naught 3 over 4, which gives us 3/8 I naught. Okay, so the important thing, again, to remember for these problems, now that we've done a couple, is to remember what this angle theta is. It's the angle between the light coming in and the polarizer. And then also the other thing that trips a lot of people up is this I naught. This I naught, like I said, does not just refer to your initial unpolarized light. It refers to the I naught that's about to pass through that polarizer. So our initial unpolarized light, we said, had intensity I naught. It passes through this filter, gets decreased now to half of that. And now that new value is the I naught for our second filter. So that's why I plugged in 1/2 I naught here for our second filter, because it's the initial light that's about to pass through the second filter. So that's important to keep in mind when you have multiple filters, especially if you have like 2 or 3. Make sure that you basically do this equation for each one, where you have your I naught, you do this equation, you get a new intensity. Then that intensity becomes your next I naught, and then you just keep going down the line for however many polarizers you have. Okay, so now let's do another example here. Unpolarized light of intensity 23.2 watts per centimeter squared is incident on 2 polarizing filters. The axis of the first filter is at an angle of 23.8 counterclockwise from the vertical, and the axis of the second filter is at 59 degrees counterclockwise from the vertical. What is the intensity of the light after it has passed through the second polarizer? Okay, so this is pretty much the same as what we were just doing. So let's do our first polarizer, and then we have our second polarizer. And sometimes also you'll see the first polarizer referred to as the polarizer and the second one referred to as the analyzer. I'm personally not going to use that terminology. I'm just going to call them both polarizers and just call them first and second. But just in case if you come across a problem that talks about the polarizer and the analyzer, it just means the first polarizer and the second polarizer. Okay, so we have here, we have our unpolarized light coming through over here with some intensity 23.2 watts per centimeter squared, and it's coming this way. Then this is at an angle, so our vertical is here, and this one is at an angle of 23 degrees. I'll call that theta 1. So theta 1 is 23.8 degrees counterclockwise from the vertical. And then, so the light that comes out of there is going to be polarized at that 23 degrees, 23.8 degrees. And then when we go through the second filter is 59 degrees from the vertical. So that will be like this maybe. So this is theta 2. Theta 2 is 59 degrees. Okay, so what is the intensity of the light after it has passed through the second polarizer? All right, so from the unpolarized to the first filter, we know that that's just going to be 1/2 again, right? So we have the initial light. Oops. So we'll say the first polarizer will just give us 1/2 the initial, and then when we go from the go through the second polarizer, we're going to have this equation, where I naught now is that 1/2 I naught, because it went through the first polarizer already. So we have 1/2 I naught, and then cosine, and then the theta we want to use here is the difference between these two angles, right? Because now this light is polarized at 23.8, so we want the angle between this light and that 59 degrees, right? So this this angle here is 3.8. This angle is 59, and we want this angle right in there. So we're just going to do 59 minus 23.8, and that will give us 35.2. So we just plug in 35.2 degrees here, and then we get 1/2 of, let's plug in 23.2 is the initial intensity, cosine squared of 35.2. Plug that all into your calculator, and we get 7.75 watts per centimeter squared. Now here, even though the intensity was given to us in centimeters squared, we didn't need to change it, right? Because we're just looking for the final intensity. So our units, we didn't have to change anything there. So our final answer is in watts per centimeter squared, and that's it. Okay, so now let's go on to, you can also polarize things besides just a polarizing filter. You can also polarize things by having them refract or reflect from some material. So the first thing we need for that is what's called the Brewster angle. So the Brewster angle was just discovered experimentally. This wasn't like a theoretical development or anything. This guy Brewster obviously discovered that there are certain angles where the reflected and refracted rays are perpendicular. So if we have some material here that has some index of refraction, and I have my light coming in like that, then it will reflect off here, and then the refracted ray, I kind of drew that so that you can't really see. Okay, so let's say that that's the refracted ray. And this is our vertical. So at the Brewster angle, the reflected and refracted ray are perpendicular. So that means that this is perpendicular here, right? That's a 90-degree angle. And we're going to call that theta B for Brewster. And now you know that obviously this is a vertical line, so that means it's 180 degrees, right? From here to here is 180 degrees. So you know that if this is 90, that means that theta B plus theta, or theta Brewster plus theta refracted are going to be equal to 90, right? Because if this angle is 90, that means these two together have to be 90, so that you get up to 180 for that vertical line. So at the Brewster angle, the Brewster angle is obviously the same here because your law of reflection. So your Brewster angle and your angle of refraction add up to 90 degrees always, just because that's the way the Brewster angle is defined. So this will be true whenever you're dealing with the Brewster angle. So now we can write this as a formula. So here, the Brewster angle is also called the polarizing angle, and that's because when light hits some medium at the Brewster angle or the polarizing angle, it will get polarized. So your reflected light here will actually be polarized, even if you send in unpolarized light here. So that's why the Brewster angle is important, obviously why it's also called the polarizing angle. So here we call it theta P. I'll just write that theta P and theta B from the previous slide are the same. So this just says that the tangent of your Brewster angle or your polarizing angle is just equal to the index of refraction of the second medium divided by the index of refraction of the first medium. And now we can just derive this because we know from our Snell's law, we know that NA sine theta A is equal to NB sine theta B. And I'll just draw it quickly here. So this is theta B, this is theta A, this is NA and NB. Sorry, this should be a lowercase b. Okay, so now we know that our Brewster angle, remember we said our Brewster angle and the angle of refraction will be equal to 90 degrees. So here, this theta A is equivalent to our Brewster angle here, and because of the law of reflection, we know this is theta A and this is theta A. So what I can do is I can rewrite, theta B here, which is my angle of refraction. My theta R, I have a lot of different subscripts, but my angle of refraction I can rewrite as 90 minus the Brewster angle, right? So I'm going to rewrite this as NA sine theta A and B sine 90 minus theta B. And then I'm also, this theta A is my Brewster angle, right? Because I said it's coming in, theta A is the angle of incidence, which in this case is the Brewster angle. So these are all theta capital B. Again, I apologize for the confusion in subscripts. So now I can think back to my trig identities and remember that sine of pi over 2 minus theta is equal to cosine theta. So I can now rewrite this sine as a cosine. So I can just rewrite this as cosine of my Brewster angle. And now I can also remember that sine over cosine is tangent. So I can divide now. So I have NA sine theta B. If I divide both sides by cosine, I can see that I'll get a tangent on one side. So I'm going to divide both sides by cosine. And then I'm also going to divide both sides by NA to get that NA over to the other side. So now I have this side has a tangent. So now I have tan of my Brewster angle is equal to NB over NA, where obviously the cosines here cancel. And that's my equation that I just had. Okay, so that's how you derive this equation that we had here. Now, typically we're going to be looking for this angle. So normally we're going to be taking, have the tan inverse, right? So normally we're going to want to find what is theta B, and we'll be taking the tan inverse of both sides. So typically we'll be seeing it this way, but we're going to do a problem with that in a second, so don't worry. Okay, so let's do an example here. So we have sunlight reflects off a smooth surface of a swimming pool. For what angle of reflection is the reflected light completely polarized? So again, when you see that, when the reflected light is polarized, that means that it's incident at the Brewster angle, right? When it comes in at the Brewster angle, your reflected light is polarized. So basically, they're just asking here, what is the Brewster angle, or the polarization angle? So let me just draw a little picture here. So this is the surface of our swimming pool. We have the ray coming in like this, and we want to know for what angle is it completely polarized. So what is our Brewster angle here? And we know that the index of refraction of our first medium, which is air, we're just going to take to be 1. And our index of refraction for the second medium is water, which is 1.33. So we can just look right back here to our equation where the Brewster angle is given by the, we have tan theta B is equal to NB over NA. And we just need to take the inverse tangent to find this angle now, right? Because we have the two indices of refraction. So we just take the tan inverse of both sides, where we get NB over NA. So let's just plug both of those in. So we get NB is 1.33, we said, and A is 1. And then just do tan inverse of that. And this is 53.1 degrees. So this is our Brewster angle here. And it's important here, we're doing everything now in degrees. So I know for our first couple chapters, everything was in radians, but now we're back to doing everything in degrees. Okay, so now for part B, we want to know what is the corresponding angle of refraction. So, how much did the light refract when it went into the pool like this? So what is this here? Well, that part is easy because we know that the Brewster angle plus the angle of refraction will be equal to 90 degrees. So all we have to do is solve for theta sub r. So theta sub r is 90 minus the Brewster angle. Which is just 90 minus 53.1. So we get 36.9 degrees for our angle of refraction. Okay, so that's it for part A and B. So now for part C, we have at night an underwater floodlight is turned on in the pool. Repeat parts A and B for the rays from the floodlight that strike the surface from below. So now we have the light coming actually from below, and we want to find the Brewster angle for that and the angle of the corresponding angle of refraction. So let's just add in another page. Okay, so let's draw a picture again just so that we know what we're looking for. So this is our medium here. Now the light is coming in from down below here. Some of it is getting reflected back and it's polarized. And then we have our vertical. And then some is getting like refracted out. So we're going to be looking for this, and then our angle of refraction now is up here. Okay, so this is almost exactly the same as part A, but now we have, we still have 1.33 in the water, obviously, and n is equal to 1 in the air. But now, when we do, so we have tan. So now when we take the inverse, so we have tan inverse, now our NB is 1, right? Because now it's the second medium. So now NB is actually 1 because the light is starting off in the water and then going to the air as opposed to starting in the air and going to the water. So now we have 1 over 1.33. So now this gives us an angle of 36.9 degrees. So this is our Brewster angle now. And then what is the corresponding angle of refraction? Well, you can kind of guess what it's going to be, but let's just do it the full way so that we're sure. So we know that the Brewster angle and the angle of refraction will be equal to 90. And now we have 30, oops. So our angle of refraction will be 90 minus 36.9. And so we're going to get for our angle of refraction, we're going to get 53.1 degrees. So you can see here that our angles are the same, but just flipped now. So what was the Brewster angle before is now the angle of refraction. And what was the angle of refraction before is now the Brewster angle. And if you want to prove that to yourself using trig, if you know some things about tangent, you can do that and prove to yourself that if you just swap the indices of refraction, this has to be the case. But obviously, in most cases, it would be easier just to sort of just do it the somewhat long way so that you're sure of your answer. Okay, so that's that. So all of our Brewster angle problems are pretty much going to be like this. We're not going to do anything too difficult with Brewster's angle. So this is maybe a more multiple choicey type midterm problem rather than a short answer. Okay, so now let's move on. Okay, so I didn't have to add a page. Anyway, okay, so now let's talk about some different types of polarization. So you don't have to just have like vertical polarization where it's just in the y direction or just in the z direction. You can have what's called circular polarization. Okay, so circular polarization just means that if you have like, let's say your x and y here, it just means that instead of the electric field vector just being stuck in like one direction, like just the y direction, it will actually trace out a circle and it will move in a circle as time goes on. So you can see here, this is sort of, like a circular polarization. You can see that the wave sort of circles. This isn't the best illustration, but, it just means the vector is tracing out a circle in some plane. So you might see, you could see it written where the electric field is like cosine kx minus omega t in the j hat plus sine kx minus omega t in the I hat. And this will just trace out a circle in the I hat and j hat direction. So you might come across this in some problems that you do. But really all it just means is that your electric field, instead of just having one set vector where it's like just j hat, it just has a second vector, with I hat or something like that, or k hat. But again, we're not going to really be doing too many problems with this, maybe one on the homework. Anyway, so this is just circular polarization. And like I said, you can also have elliptical polarization where essentially the electric field vector traces out an ellipse instead, but we're not going to do anything with those problems. And I also, for this optics section, and actually a lot of the optics sections that we're going to be doing, I would definitely recommend looking at that Halliday-Resnick book. So there's a link to a PDF on Piazza. I think the first Piazza post we had was someone posted a link to that book. I think their optics chapter, it's in a little bit different order than we do, but still all the content is there. I think it's way better than our book. I really don't like the way our book handled the optics section. I think it was sort of unnecessarily confusing in some places. So I definitely highly recommend looking at the Halliday-Resnick book instead. So if you want to look at that book, I highly recommend it. So then just briefly scattering. So why is the sky blue? Well, we know that our sun sends us unpolarized white light, obviously. So we get unpolarized light from the sun, and then the molecules in our atmosphere oscillate in such a way that they mostly scatter blue light. So that's why we see the sky being blue during the day, is because the molecules in our atmosphere are very effective at scattering the blue light wavelengths of the light that comes to us from the sun. Now, again, if you take like a graduate electrodynamics class, you actually can like do these calculations and see that that's the wavelength of light that gets most effectively scattered. Obviously, that's way beyond our scope. So, just knowing that the air molecules scatter blue light most effectively, and that's why we see the sky as being blue, is sufficient for our case. Okay, and then let's just look at Huygens' principle. So Huygens' principle is just basically a geometrical method for determining the shape of a wave. If you know the velocity and the shape of a wave at one moment in time, you can then determine the shape of the wave at some later moment in time. And you can use this to show the law of reflection. We're not going to do that because it just would take a really long time. So basically what Huygens' principle says is that each point on your wave acts as like a wave source for secondary waves that travel at the same speed as the original wave. And if you trace out these secondary waves, you can find basically like the new wave front. So here's a picture. So you have some initial wave front here, and then you treat each point on the wave front as a new source of waves moving at that same velocity v, whatever they were moving at. And then, so this point makes a new wave front here, this point makes a new wave front here, this one, and so on and so forth. And then you basically can draw like a tangent to sort of all of these wave fronts, and that gives you your new wave front. Now, you can also use this to explain why you see mirages, but personally, I've never seen or used Huygens' principle outside of this one section of 7E. I didn't come up at all on the physics GRE. I've never used it in any other scenario. So this is all we're going to do for Huygens' principle because, I don't really think it's that useful, honestly. So what we're going to do instead is do some challenge problems. So since this chapter 33 doesn't really have like that much content compared to some of our other chapters, so I'd rather do instead is just do some more challenging problems, so you really understand and really know well the content that we do cover from chapter 33, since there is a little bit less, I think, content-wise. So let's do this problem. Okay, so for this problem, when the sun is either rising or setting and appears to be just on the horizon, it is in fact below the horizon. The explanation for this seeming paradox is that light from the sun bends slightly when entering the Earth's atmosphere, as shown in the picture below. So it bends a little bit when it's entering in the atmosphere. Since our perception is based on the idea that light travels in straight lines, we perceive the light to be coming from an apparent position that is an angle delta above the sun's true position. So we are going to make the simplifying assumption that the atmosphere has a uniform density, which obviously it doesn't. We're going to say it has a uniform density, and hence a uniform refraction of index, we'll just call N. And then it extends some height h above the ground and then just immediately stops. So obviously our true atmosphere kind of tapers off a little bit and the index of refraction changes. We're just sort of going to treat it as just one solid atmosphere that just ends abruptly at height h and has just one index of refraction to make the problem easier. So we want to show that this angle delta here can be given by this expression where n is the index of refraction of the atmosphere, capital R is the radius of the Earth, and h is the height of the atmosphere. So the first thing let's do So the first thing we want to do is let's draw a picture. Okay, and here is a little schematic of what's going on. So just to recap here, so this is the atmosphere in here. This is the radius of the Earth out to here. And then this is our angle, our sun is coming in at this angle delta. So now the thing to be careful of here is that we want to get our normal, right? When we talk about refraction, we need to have a normal to our surface. So we're going to say that our surface is like tangent to the, and that doesn't really look tangent, but our surface is tangent to the atmosphere at the point where this ray enters the atmosphere. So this ray of sunlight enters the atmosphere right here. So we're going to look at a tangent on the atmosphere. That will be our surface. And then our normal comes out of that tangent. So pretend that doesn't really look normal to my tangent, but pretend it is. So this is normal to that tangent of the atmosphere like that. And then we have this angle theta A is going to be our angle of incidence, right? Because this angle, this ray is coming in here, so we measure it from the normal to the surface. So theta A is our angle of incidence. And then theta B here is this angle. So once this ray comes in here and bends when it enters the atmosphere, it makes a little triangle here. So we have this is the radius of the Earth. So this ray of light is going to meet the surface of the Earth somewhere, right? So it's going to meet the surface of the Earth here. And then we can create a triangle with the point where it enters the atmosphere. So we have just a nice little triangle here. And then from our intro to geometry class, this angle is going to be the same as this angle, since we have this perpendicular line going straight through, and then we have this straight line here. So this angle and this angle have to be congruent. Okay, so now that we have that all set up, and then let's see. And then we also know here that our angle delta is going to be this full angle, the angle of incidence theta A, minus this angle theta B, right? That will give us delta left. So delta is theta A minus theta B. So let's first use Snell's, so So let's first just use some basic trig to find theta b, because we have a nice triangle here, and this is a right angle. So we have a nice little triangle here where we can just find theta b using just trig. So let's do that. So we have, we want to find sine of theta b, and we have so sine theta b, sine is opposite over hypotenuse, right? And we have the opposite is this side, the radius of Earth r, and the hypotenuse over here is r plus h. So sine theta b is just r over r plus h. And now I can take the inverse of both sides to get an equation for theta b by itself. So theta b is sine inverse of r plus h. Okay, so now, we're almost there. So now we just have to find theta a, right? So now let's use Snell's law to find the angle of incidence, because now we know the angle of refraction, theta b, and then we can find theta a using Snell's law. So now we're going to use Snell's law. So we have NA sine theta a is equal to NB sine theta b. So let's solve for theta a first. So we'll have sine theta a is NB over NA sine theta b. And then we're going to take the sine inverse of both sides. So we'll get theta a is NB over NA sine theta b. And then this is all sine inverse. Okay, so now let's simplify a few things. So we have sine of theta b, but we know what theta b is, right? It's sine inverse of r over r plus h. So sine of sine inverse r over r plus h is just r over r plus h, right? Because when you have a sine and then a sine inverse, those cancel each other out. So we're left with just r over r plus h. So this comes out to sine inverse of NB over NA times r plus h, right? Because this sine of theta b is just r over r plus h. Okay, and now our NA, so our initial index of refraction, we know is just 1 because it's out in outer space where, the index of refraction is just 1. So we can replace this with just 1. So we have just NB here. Okay, so now we have theta A. So now we can just find delta because we said delta was theta A minus theta B. So let's just write that all out. So delta is theta A, which is sine inverse of N, which is, we'll just call it N, is the index of refraction of the atmosphere, R over R plus H minus theta B, which is sine inverse of R over R plus H. And that's exactly what we wanted to get, what the problem asked us to find. So they wrote it as arc sine. We have it as sine inverse, obviously same thing. But you can see that our two answers are the same. So that is the angle delta there. Now they want us to plug it in some numbers. So they give us the radius of the Earth in kilometers. They give us the index of refraction of air is 1.0003, and they give us the height of the atmosphere is 20 kilometers. So you can just plug those things in, make sure you convert kilometers to meters. Just plug those numbers into this formula, and you'll get a number for delta. So that number, if you plug those in, comes out to 0.23 degrees. So that's obviously very, very small. And they say here, so once you calculate delta, how does this compare to the angular radius of the sun, which is about 1/4 of a degree? So that means when you look at the sun in the sky, it looks like it takes up about 1/4 of a degree in the sky. So if the sun is about 0.25 degrees and this delta here is 0.23 degrees, those are almost the same. So what this is telling us is that this delta here, so like the difference in the apparent position of the sun from where the sun actually is essentially the same distance, the same size as the sun itself to our eyes from Earth. Okay, so this was like a challenge problem. I definitely, even though I wouldn't ask you something this difficult on the midterm, it's definitely very, very useful to go over because you will really learn the material, obviously, by doing harder problems. So I really recommend making sure that you understand how to do this problem. This is like a very good challenge problem. Okay, now let's do one more slightly challenging problem. This one is, I think, a much more reasonable challenge problem, so something like this could turn up on the midterm. Okay, so here we have a beam of light traveling horizontally is made of an unpolarized component with intensity I0 and a polarized component with intensity IP. The plane of polarization of the polarized component is oriented at an angle theta with respect to the vertical. So we have some vertical here, and then our polarized component IP is making some angle theta with that. Okay, so here we have a graph. Is the total intensity after the light passes through a polarizer versus the angle alpha that the polarizer's axis makes with respect to the vertical. So that means then our polarizer is like making some angle here where this whole thing here is alpha. So what is the orientation of the polarized component? So what is theta? And what are the values of I0 and IP? So the intensity of the unpolarized light and the intensity of the polarized component. Okay, so the first thing we want to do here is write an equation for the total intensity that we see after the light passes through the polarizer. So we said that it's made up of some initial light that's unpolarized. I'll write it like this. We have the unpolarized plus the polarized. So the unpolarized, after it passes through a polarizer, we already know what the intensity of the unpolarized light will be after it passes through that polarizer, right? It'll be 1/2 I0. Then for the polarized component, we know that that will be I0 cosine squared. We'll call this phi, where phi is this angle between the polarized light and the polarizing filter. So we'll call that phi is alpha minus theta. Okay, so I'll write that over here. So phi is alpha minus theta. Now this part is going to be the same for all angles, right? We said it doesn't matter what angle the polarizing filter is at, the intensity of unpolarized light going through will always just be 1/2. So that we don't have to worry anything about. Now this one, we know where this term is going to be a maximum and a minimum, right? It's going to be a maximum when cosine theta is equal to 1. Sorry, cosine phi, I'll say. When cosine phi is equal to 1, and that happens when phi is equal to 0 degrees, right? And then we know that there will be a minimum, so this term will be a minimum when cosine phi is equal to 0, and that happens when phi is 90 degrees. And now the reason why the minimum wasn't -1 here, why we said 0 instead of -1, is because we're squaring the cosine. So if we had said that a minimum was when cosine phi was equal to -1, that would actually correspond to a maximum, because when we square -1, we obviously get 1 again. So the minimum is when cosine of phi is 0, not -1. Okay, so let's look at when this is a maximum. So we have a maximum here. Now, again, this graph, like, they could have put some vertical lines because it's a little bit hard to decide where exactly this is. Let's say this is around like 35 degrees. Obviously, if I gave you something like this in the midterm, I would make sure that it's like easier to read the plot, because it's not clear if this is 35 or 40 or 32 or 28. So we'll just say 35. so there's a maximum there at 35 degrees. And this is alpha here. So we have this maximum when alpha is 35 degrees and the intensity was about 25. So we said a maximum happens when phi is 0 degrees, and we said that phi was alpha minus theta. So if we want, let's write it this way, we want, at our maximum, we want alpha minus theta to be equal to 0, and alpha is 35. That means that theta is also 35, right? So that we get to 0. So here at our maximum, theta is 35 degrees. So this is our angle theta. Now let's just check also at the minimum, but also because we're going to need it to find the intensities. So let's just check at the minimum that we get the same answer. So let's see where the minimum is here. So the intensity minimum is about right here. So that looks like it's about halfway. So let's say that that's 125. Alpha is 125 here. So we said at a minimum, we want this alpha is about 125. The intensity was about 5. And we said that at a minimum, phi is 90. So we have 90 is equal to alpha, which was 125, minus theta. So again, here we see that theta being 35 will give us the correct answer. So at alpha is 125, if we subtract theta is 35, which we just found here, we do in fact get 90, which would give us a minimum of the intensity. So theta makes sense as 35 there. And now we can use these to find the intensity. Okay, so let's find the intensity. So we had this equation up here. Sorry, this should have been P, because the intensity of the unpolarized light was I naught, and the intensity of the polarized light was I sub P. So I should have written I sub P here. Okay, so now let's find, we want to find I sub naught and I sub P. So let's look at the minimum first. So when this cosine is at a minimum, right, when we have cosine of phi is equal to 0, this term will just be equal to 0, right, and none of it will get through. So that means that we have the total intensity that gets through is just that 1/2 of I naught. And we said at the minimum we had 5 watts get through, 5 watts per meter squared get through, and that's equal to now 1/2 the intensity of the unpolarized light. So we can see that the unpolarized light has an intensity of 10 watts per meter squared. Okay, so that's our intensity of the unpolarized light. Now the intensity of our polarized light, we can look at the when it's at a maximum, so the cosine term will be equal to 1. So then at our maximum we had, so this is for the min and this is for the max, I total will be 1/2 I naught plus IP, because then this cosine squared, like I said, is equal to 1. So at the maximum, on the graph, we said that the total intensity was 25 watts per meter squared at our maximum. Then we have the 1/2 times 10 plus IP. So we have 25 is equal to 5 plus IP. So we can see that the intensity of our polarized light is 20 watts per meter squared. Okay, so that's it for this problem. Now again, this is a really good problem because it combines kind of a lot of things for the intensity. So this is a really, really good problem to make sure you study. You know, something like this is definitely midterm worthy. So make sure that you can do a problem like this with this polarizing stuff. Okay, so that's it for today. We'll continue next week with chapter 34, and then don't forget, after chapter 34 is our second midterm. So we have chapter 32, 33, and 34, and then midterm 2. Okay, so that's it for today, and I will see you guys next week.